Hello, I'm Sean McGee, and I'm an astronomer and a faculty member at the University of Birmingham. I research how galaxies form and evolve through cosmic time, from the Big Bang at the beginning of the universe all the way until today. In this talk, I'll tell you about a new type of galaxy that astronomers have found, and which are called ultra-diffuse galaxies. I'll then discuss these galaxies and whether they're a challenge for what we know about the universe and how galaxies form. A slight spoiler alert is that we don't have the answer, because this is still an active area of research. So if we go in to see what a normal spiral galaxy looks like, it has a distinctive arm pattern like this one, and like the one behind me, with sort of bright patches where current star formation is happening. These galaxies tend to be much brighter near the center than in the edges. In a sense, they're more concentrated towards the center. They have this concentration. But they're also fairly bright all throughout the entire galaxy. You can easily pick them out against the background, and they make the nice images that people see. So in the last 5 years or so, astronomers have sort of characterized another kind of galaxy. It's been known a little bit before that, but it's only recently that we've really got these in large numbers. And this is shown in this picture in the middle. You may notice a sort of faint, fuzzy kind of galaxy in the middle. It clearly looks sort of different than that first galaxy. These two galaxies have about the same physical size. The images are sort of scaled similarly. But a normal galaxy is much denser and brighter than this ultra-diffuse galaxy. And it's this feature that makes this galaxy called ultra-diffuse. It seems much more spread out than normal. And as I said, I'll talk about whether or not this is a challenge to galaxy formation. But before I can discuss why this kind of galaxy is unusual, I'll describe first about how normal galaxy formation happens. And there's really two elements to galaxy formation. The cosmology part of it, or what our universe is sort of made of. And then what is also sometimes called gastrophysics. And that's really sort of the astrophysics of normal matter like gas. It involves a lot of different, very complicated physics, if we're honest. Kind of like the formation of stars, the radiation that such stars give off to their environment, and the energy that these exploding stars give to their surrounding gas. And even things like the exotic effect of, say, matter falling into a black hole, getting heated up and just sort of spewing back out. So we'll look at each of these in turn, ultimately understanding how normal galaxies form. So the first tenet of this is cosmology. You may have heard that our universe has only about 5% of its total energy densities in normal matter. And that includes things like, the sun, the moon, trees, and chairs. These clearly have a big impact on our lives and also about how galaxies form. But for the most part, a large part of galaxy formation is caused by gravity. And that gravity is really dominated by dark matter, the stuff we don't see. And where the stuff we see, the ordinary matter, is really like a frosting on top of that. So we'll first talk for a minute about dark matter. Since it's sort of the dominant cosmological force on galaxy formation. So this is an image taken from a numerical simulation, which can follow the growth of a substance like what we think dark matter is. When these simulations are done, it turns out that dark matter, if you just let it be and form through gravity, clumps together in a very particular form called a halo. Notice each of these sort of spots in the image, or these clumps. These are each collapsed halos that have formed out of initial very smooth matter density distribution in the very early universe. Those very small ripples that happened in the early universe, these initial seeds that eventually formed these halos, is really thought to be caused by tiny, tiny quantum mechanical effects, which were essentially blown up into a massive size through the process called inflation, which I won't talk about. And those really form the basis of the galaxies we know today and the collapsed structures. And we believe basically that every galaxy forms at the center of a dark matter halo. And this is one of the central tenets of galaxy formation, and something that may be, challenged by ultra-diffuse galaxies. But it's first useful to sort of understand what the evidence for dark matter is. I mean, astronomers say it exists, but you shouldn't trust anyone based on just their opinion or what they state. You need to see the evidence behind it to see if you follow their reasoning. And the evidence for dark matter really started to convince at least the bulk of astronomers that dark matter was real, and it came from the work on rotation curves by astronomers such as Reuben, who's shown here in this picture. In the 1970s, these astronomers made really careful and crucial measurements of how fast stars moved around the center of a spiral galaxy. And the speed of those stars moving in the galaxy tells you exactly how much sort of gravitational force they're experiencing from the matter closer to the galaxy's center. If a star moves faster in a galaxy than the gravity can maintain, it will just fly out of the galaxy. And you can kind of think of this like a person being spun around on a carousel. If you spin them too fast for their grip to hold on, they'll just fly off the carousel, which is not something I'd recommend, but And so by necessity, if you see stars spinning around, they can spin no faster than the gravity can hold them, else like the person in the carousel would have flown off. So in this plot on this slide, you can see the circular velocity, that is how fast stars are spinning, versus the distance to the center. The data points are the black points that you can see. And it turns out that you can't explain those black points, that is the rotation speed of stars around a galaxy, if the only material in the galaxy is the stars. If that was true, you'd predict a rotation speed that would fall off pretty dramatically with radius, get slower and slower, as the sort of disk line in this plot shows. The data seem to require an additional mass component, and here that's labeled as halo to explain the data. This halo, you can't see it through a telescope other than this kind of indirect effect. And this is really the beginning and the basis for dark matter and what we call dark matter. Although it's popular to talk about galaxy rotation curves as the reason for believing there's dark matter, I should note that there's also dark matter has sort of beyond those the evidence for those has really become sort of overwhelming from different observations. And more generally, all different aspects of our current cosmological model are really well understood. So today we know about things like dark energy from the brightness of supernova explosions and their brightness as a function of the distance to them. We have good evidence that the dominant gravitational force of cold dark matter really dominates the large scale structure. And we can see that both in simulations and observations and comparing the two. Similarly, the cosmic microwave background gives us a picture of the universe soon after the Big Bang and sort of before any of these large scale structures have collapsed. Our cosmological model really seems to all fit together, and together with the abundance of elements that are predicted by Big Bang nucleosynthesis, that is the production of elements soon after the Big Bang, when the universe was very hot and dense, they all really fit together well. And the interesting thing is that they all probe quite different circumstances in the universe. If you think of the Big Bang nucleosynthesis, it's right after the Big Bang where the universe is very hot. The CMB, or the cosmic microwave background, is sometime later, but in the very flat stages of the universe. The large scale structure is essentially today, and the supernova you can see throughout time. All of those things sort of come together to make the cosmological model we know. And so it's important to realize that disproving sort of one part of that thing will still leave the whole sort of relatively cohesive. And so that's what why we call our cosmological model the concordance cosmological model, because everything sort of seems to fit together pretty well. So now I'll talk briefly about the other side of galaxy formation, and namely the gastrophysics part. This is an image of a region of forming stars, and you can immediately see how it's very complicated. There's swirling dust clouds and strong clusters of emission, which is the basis of star formation. And so overall, the cosmology sort of describes how dark matters grow and in what abundance. But what happens after that in the galaxies is really the realm of this thing called gastrophysics. So mixed almost uniformly through the dark matter halo at early times is this gas, which makes up the normal baryons and the normal stuff. The interesting thing about that normal material, unlike, say, dark matter, is that it can interact with itself and also give off photons. This means that the gas and the normal material can ultimately cool. And when a gas cools, the individual particles stop moving as quickly. And as they do, they no longer orbit as quickly through the dark matter halo and tend to sink to the bottom and sort of clump together. This means that, with time, as gas cools, it will clump towards the center of the halo. And if it cools enough and clumps enough, it'll eventually be dense enough to form individual stars. These stars then ignite nuclear fusion in their center. And with the accumulation of those enough gas and future star formation, the halo essentially hosts a galaxy at its center. The accumulation of those stars is a galaxy. And with time, the more gas cools through these processes and the galaxy grows bigger and bigger. And at some point there, the galaxy naturally begins to look a bit like a spiral galaxy with a bright center where all the stuff is sunk towards and arms of star formation swirling around it. There's a whole wide range of other aspects of galaxy formation that come into play here to determine exactly what these look like. Galaxy formation is not a solved problem or a solved field, and there's lots of things that happen. But some of those are explosive things like we talked about earlier. For instance, this image of this particular galaxy looks mostly like a normal spiral, except that you can see these great hot plumes of red gas coming out perpendicular to it. This gas is expelled from the galaxy and outflows. These outflows are thought to be from things like internal feedback mechanisms, sort of like supernova explosions or this black hole emission that I talked about before. Ultimately, in a detailed process that we don't fully understand, galaxies tend to form a very regular structure that falls on sort of consistent scaling relations like the one shown here. This plot shows the size of a galaxy on the y-axis versus the total luminosity of the galaxy on the x-axis. The two types of galaxies, early, meaning sort of round and elliptical galaxies, and late, which sort of mean like a spiral galaxy. They both have well-measured relations, which are pretty similar to each other. And you can see that a brighter galaxy, so you go to this side of the plot, tends to be bigger and is consistent through a wide range of luminosities. So the same relation seems to hold throughout the whole range of luminosities. So somehow these aspects, the gastrophysics, the detailed structure, and cosmology work together to produce these galaxies. And we think we have a reasonable understanding of why that is. But these are very fundamental parts of astrophysics, right? Gas physics and cosmology. So when something sort of weird shows up, it's very exciting. And now I can talk about ultra-diffuse galaxies and what they are and how they were found. This plot is similar to the one I just showed. It plots the size of a galaxy versus the total luminosity or the brightness of the galaxy. These gray points are sort of normal galaxies and the kind I showed on the previous plot. The surprising thing is these red points. They're what's called ultra-diffuse galaxies, and you can see they have a larger size than you'd be expected from their brightness. Right? See, they're up in this region. And although galaxies of this type have been known for a little while, a new kind of telescope called the Dragonfly telescope started to find and measure these galaxies in really large numbers. And so now these galaxies are actually routinely found all over the sky thanks to improvements in sort of data reduction techniques and as well as sort of a concerted effort to figure out what they are. And if you remember a couple of slides ago, I said one of the characteristics of normal matter in a dark matter halo is that it sinks to the bottom and forms a concentrated object. These very broad, diffuse nature of these particular galaxies then maybe points to them as strange objects. Why aren't they more concentrated? There's lots of interesting aspects to these galaxies, but one of maybe the most exciting is that people have suggested they don't form inside of substantial dark matter halos like most galaxies. If we remember back earlier, the initial evidence for dark matter from Vera Rubin came from measuring the speed of stars around the galaxies. In this case, our current telescopes can't actually measure the individual stars. They're too faint. But luckily, we have objects called globular clusters, and these are very, very packed, dense regions of stars. And in this case, they sort of clump around and through ultra-diffuse galaxies. With today's telescopes, we can measure the velocity of each of these clumps and try to tell how much matter must be holding it together within the galaxy. These globular clusters are shown in the image, and they're noted sort of by these individual numbers. You can probably just make them out as like bright points on the plot or the image. And so if you go and measure the velocity of each of these globular clusters, you can get a dispersion of velocities around the galaxy. That is, some are a little bit in front and moving towards, and some are a little bit away and moving back. And that dispersion tells you the total mass in the same way that the velocity around the galaxy does. And so here's a histogram of the velocity of each of these clumps, that is those globular clusters. And the red line is a fit to the data. And it suggests that they're only moving around the galaxy at about 8.5 kilometers a second. So, 8.5 kilometers a second sounds very high. In the context of galaxies, it's actually really pretty slow and suggests that there isn't much mass within this galaxy. A way of seeing that is in this plot, which shows the velocity dispersion versus the mass of the stars in the galaxy. This is shown for a wide range of systems, but the particular galaxy that we're talking about is shown here around the 8.3 stellar mass mark. Notice this dotted white line. This is the velocity dispersion that'd be expected if the velocity was only due to the mass of the stars that we know about, the ones that we can see. In other words, that there's no dark matter in this galaxy. That would be the implication. And that's sort of the implication that we have at the moment. Another way of seeing that is in this plot, which shows the velocity dispersion together with these sort of shaded regions, which is where you'd expect the galaxies to be if they contained only stars on this side, or if it had a normal dark matter halo and looked more like a normal galaxy. It should have a higher velocity dispersion up at this area. And so this is a very active field, active area of study, because it's potentially so exciting. And so you can see there's also been 2 further studies of this galaxy, these 2 other data points with different techniques, but which verify the velocity dispersion measured. So it's clear that it wasn't just a fluke of that one particular measurement. We think this is really that velocity dispersion. And this really suggests that, dark matter doesn't exist as much in this galaxy as we'd expect, which is really exciting. But perhaps even more exciting, because there's you can always explain one object maybe. More exciting is that there's a second ultra-diffuse galaxy which has been found, which also seems to have a lower than expected velocity dispersion and may point to dark matter not existing in that galaxy. The lines in this plot show the expected velocity dispersion, which comes from analyzing this new data. And the red line is what is expected if only the stars exist in the galaxy. Again, this seems to be another galaxy which just lacks a dominant component of dark matter, which really suggests maybe in general, these ultra-diffuse galaxies don't host dark matter, which would be very exciting. And so these findings are very exciting, but it's still an open area. This is relatively early days on this study, and we don't know yet exactly what's driving this formation of these galaxies. Although there's many possible explanations. For instance, you could imagine that the galaxies are simply failed Milky Ways, that for some reason they haven't formed as many stars as you'd normally expect for their size. Although this might explain them sort of generally, their processes, it wouldn't explain why they seemed to have no dark matter. If it was just a failed Milky Way, you'd expect the dark matter halo to still be there, but just the number of stars to be fewer. And doesn't seem to be the case. Another explanation for this could be that they were disrupted by other galaxies, which essentially puff them up by interacting gravitationally with them. That's possible. Another explanation is that some kind of internal processes, maybe like this black hole feedback, has caused the galaxies to form very differently. For some reason, these particular galaxies maybe have formed differently. Fortunately, neither of those two explanations would explain why there's a lack of dark matter. If there was some internal process that stopped it, the dark matter should still be there. And if it puffed up by interacting gravitationally, it probably also should have a dark matter halo. And so none of those explanations are really terribly satisfying. And so it maybe leaves the question that there's something completely different that needs to happen to explain these galaxies, and maybe a complete revision of our picture of galaxy formation. Luckily, we won't have to wait too long to make a lot of progress. In the future, I expect with new telescopes and new observational techniques becoming available, that we'll find a lot more of these galaxies and really start to understand what's happening. One of the telescopes I'm personally most looking forward to is the Reuben Observatory, which is currently being built in Chile and should be available in the next couple of years. One of the first surveys this telescope will do is called the LSST, and that should be a really interesting survey for this. The telescope has a very big mirror, but can also take images of very large regions of the sky all at once, which means we should be able to detect these ultra-diffuse galaxies with, extraordinary speed and number in the near future. One of the things I like the most is that the telescope is named after Vera Rubin, who I mentioned earlier really pioneered the study of dark matter in galaxies. And so at least to me, it seems fitting that the telescope that bears her name will take these studies much further into the future. So that's ultra-diffuse galaxies. And as I said, we don't really know what happened or why they are like that, but it's a very exciting time to look into them.